last time we were here, we typed in inverse norm of 0.995, right? Does everyone see where that came from?
The left side.
Yeah, I mean, if you have a 99% confidence interval, right? How much is left over? 1%, right? So what we would say, if I just kind of go over here to the margin for a minute, we would say that the significance level, that's the leftover. Alpha is 0.01. So that's how much area is in the tails of the normal distribution. Then what you do, right, you take that 0.01 and we're going to divide by 2, right? So it's 0.01. That didn't work. Let me try again. 0.01 divided by 2. And that's your 0.005, right? So that's how much would be in each of the tails in the picture, right? 0.005 here and 0.005 here. These are called the critical regions.
You can find the critical regions every time dividing by 2.
That's a good question. I mean, so far, every time we've wanted to get the critical regions, the first step has been take that alpha, divide by 2. And for confidence intervals, yes.
Okay.
That's what will happen. The picture will be, you have symmetry. You have critical region on one side, critical region on the other. The funny thing about your question is you did say always. And in chapter 8, we're going to see sometimes we do what's called a one-sided test, and the region will just be on one side. Then you won't need to divide. But yes, so far that's true, right? Then what we need is we need the critical value, right? So the critical value would be Z alpha over 2. And again, how I did it was inverse norm, not just of 0.99, but of 0.995, because you had to add on that extra piece, right? By the way, another way to do this, when you see that 0.005, what's the Z value here? I'll zoom in. Yeah, next to that 0.005. See, let me zoom in a little bit more. Is that better? What is this Z value right here?
0.005.
Well, the 0.005, that's my area or my probability. That's not the Z score.
It's just Z alpha?
It's funny. We call this thing Z alpha over 2. I guess you might say this is negative Z alpha over 2. Because what this value is, here, let me compute it. How would I compute it? I would do inverse norm. Inverse norm. How much is to the left? 0.005. Do you know what we're going to get?
Negative 2.56.
Exactly. If I do second distribution, I'll do inverse norm again. And instead of doing 0.995, let me do 0.005. And you'll see that we're going to get the negative of the same thing. Negative, I guess it's 2.58, right? I don't know why I said 6 last time. Maybe because I was rushing. Right, if we round, that's negative 2.58. So I guess the point is, this is negative 2.58, and this is positive 2.58. So what you want to put in the formula for the margin of error, looks to me like we want to put 2.58. Okay? So we put 2.58 there. Now, P hat, Q hat, those are all the same. We didn't change those for Mendel's experiment, right? 2620, yep. So we have 0.262, and then Q hat was 0.738. And then do you guys remember what N was? 580? Okay? So actually, what I could do, I'm sure I still have it in the calculator. Let's go back to it. And so on the calculator, if I just start scrolling up, I can find where I typed it in last time. Where was it? There, right? This is basically the same calculation. The only difference is, instead of that 1.96, I need to type in 2.58. .58 is my new Z alpha over 2, and that changes the margin of error to 0.047. All right, so here I go. Back here, we just computed. We're supposed to do E. And what we got was that the new value of E is 0.0407? No, just 0.047. Maybe 0.0471, right? And now, I guess the question is, what will be the new confidence interval? If you look what I did last time, because we took, right? How did we do it last time? We took 0.262 and we added and subtracted the margin of error. So it's going to be 0.262 plus 0.0471, and it's going to be 0.262 minus 0.0471, right?
Why can you just add up and divide it by 2? Add both sides and divide it by 2?
Add what? Tell me what to add.
0.262, no. The 0.4, I can't remember.
Okay.
I know that you can add both sides and divide it by 2, and then, you can subtract it on both sides, and you can also find E that way. But my mind just went blank. You know what I'm saying? Like these.
I'm thinking about it.
Okay.
I mean, once you find E, you know that P hat is always the center of the confidence interval. And P hat was this 0.262. So maybe what you're telling me is that if you doubled this, that's how big the confidence interval would be. That's my thought about what you might be saying. But to me, this is the easiest way to do it. So now, let's type that in and see what actual values we get. By the way, what did we get last time? Last time we got 0.2262 to 0.2978. That was for 95% confidence. If you want 99% confidence, I guess my question is, what does that do to the confidence interval? Does it make it larger? Let's see. If I take the 0.262 and add the 0.0471, let's do that. Well, there's the 0.0471. So let me add the 0.262 to that. I'm at you're right. I'm above 30%. 0.3091 is the upper bound of the confidence interval. 0.3091 is the upper bound of the confidence interval. Huh. And what would the lower bound be? I guess it would be 0.262. Oops. 0.262 minus 0.0471, right? So the lower bound is 0.2149. And now I'm just comparing that to the one we had before, right? So on my paper, in black on the top, you guys can still see the 95% confidence interval. And then we said we wanted a 99% confidence interval, and I worked that out here in the brown, and I got a larger net to try and catch the parameter, right? I'm 99% confident that the parameter is somewhere between 21% and 31%, right? So if you want to be more confident, the thing is that you're going to have a wider net, so you might say that you're less accurate. If you want the confidence interval to be smaller, now your confidence is down. So there's a trade-off. And you kind of have to decide what you want for your significance level. And 5%, that's a pretty good kind of standard if you don't know anything else. A lot of times people will do a 95% confidence interval. But there are situations where we say, no, we want to be more confident, but then that means we need a wider range. I think that's interesting. So you guys have any questions on these examples we've done so far? And some of the homework problems were like this, right? I mean, where you had to construct a confidence interval. Yeah, a lot of them. There were other kinds of homework problems in this section that we haven't really talked about yet. And so I'd like to do an example of those where the question is, hey, how big should my sample be? But here's the thing, guys. Where does sample size show up in the formula? Right there, right? That denominator is your sample size. So if you get a large sample, what happens to a fraction when you make the denominator large? Like, which is bigger, 1/2 or 1/10? One half is bigger. 1/10 is smaller, right? When I make a fraction denominator bigger, I'm making the number smaller. That will shrink your confidence interval. It's kind of interesting. Okay? Yeah, but we're going to go backwards here sometimes. And so we need to talk about how that works, right? So, for example, say we want to estimate some population proportion. The question is, how many sample items must be obtained? And the answer is, we can do algebra to our basic formula and solve for n. And if we do, we get this formula. Now, if you're like me, you don't like slides like this. I mean, they're okay, but I always want to know why. Why does it work? So let's work it out. I'm going to write that formula at the top of my paper. Well, I think the first thing I'm going to write is I'm going to write finding sample size, right? So if I want to find sample size, I can start with, let's see, we know that the margin of error formula is given by z alpha over 2 times the square root of p hat q hat over n. Okay. Now, I'm trying to get the n by itself. Well, there's a lot of algebra to do here, right? So first thing I want to do is suggest that we try and get the big square root by itself. What would you guys do to both sides to get the big square root by itself? Jared, you have an idea? What number? Yeah. Oh, I see what you're saying. I think what you're telling me is, yeah, thank you. Once I have the square root by itself, you're kind of telling me what to do. Because then you'll square both sides, like you're saying. You'll be multiplying it by itself. But to get it by itself, guys, I got to get rid of this z alpha over 2. Right now, it says z alpha over 2 next to the square root. What's that mean? You put two numbers next to each other, that means multiply, right? So what are we going to do to both sides? Let's divide. That'll undo it. Here, watch this. E over z alpha over 2 is equal to square root of p hat q hat divided by n. And now, I like Jarrett's idea of kind of, hey, you want to multiply something by itself. Another word for that is we're going to square both sides. Because if I square the right-hand side, what happens when you square a square root? Well, it goes away. I get p hat q hat over n. And on this side, I now have e squared, and I also have z alpha over 2 squared. And this is some serious algebra we're doing here at this point. Except all it is, guys, it's two fractions with an equal sign. I remember learning about that actually in grade school. We called that a proportion. Do you remember what you do when you have a proportion if you're trying to solve? No? It rhymes with Moss scultiply. All right, it's cross multiply. Very good. So here we go. We have n e squared equals z alpha over 2 squared times the p hat q hat. And so, how do we get the n by itself now, guys? What do we do to both sides? Not anymore. We did cross multiply to get from here to here, so I'm up here now. We almost have the n by itself. It's just n. Right. Yes, we're going to divide by that e squared now, right? So the final little formula that I'm getting is n equals z alpha over 2 squared times p hat times q hat all over e squared. Is that the formula that they're listing for me right here? Yes, it is. It's not magic. It's mathematic. Right? Okay, so we have the formula. Now, how do we use the formula? That's what I have to show you. Okay? And actually, I wrote down a problem to try. Let's skip these little slides for now and come back. Here we go, problem 36. And then I want to talk about these formulas here. So, problem 36 in your book, if you'll turn with me, we're looking at page, well, it's just one before here. No, one more. Page 341, number 36. This is a problem involving sample size. On-time rate. It says you've been given the task. Hey, your future career, guys, when you work for the new Cleveland Hopkins upgraded airport, you have to estimate the percentage of Southwest flights that arrive on time. So if you're 10 minutes late, they count that as on time. 20 minutes late? No, it says no more than 15 minutes late. How many flights must you survey if you want to be 80% confident that your estimate is within 3 percentage points of the true population percentage? Part A, assume that nothing is known about the percentage of on-time Southwest flights. Part B, assume that for a recent year, 84% of Southwest flights were on time based on data from the Bureau of Transportation Statistics. There's a difference. Part A, you don't know as much as you know in Part B. Part B, they told me this fact. I have a question. Looking at the formula, do you know what information they gave me in Part B? It's something from the formula. You got it. Right? P hat is 84%. It says 84% of Southwest flights were on time in a survey. Right? So, if we know that, we can use the formula to do Part B. Let me try this now. Okay, so I'm going to do Part B first, because I think in this problem, it actually makes sense to do that. For problem 36, first let's do Part B. Part B, we know that P hat is 0.84. The formula I need, n equals, so what do we have? We have z alpha over 2 squared, p hat, q hat, all over E squared. That was the formula we just derived. And so, I guess, so far, I know I have the Z alpha over 2. No, I don't know that yet. Oh, what I do know is I know P hat. P hat is 0.84. Can you guys tell me anything else? I need Z alpha over 2. I need Q hat and I need E. What's that? For what? Q hat is 0.16. I agree. Let me see that. So for E or Z alpha over 2, which one you give me? You know Z alpha over 2? How'd you get that? You already did it. Okay, good. But let's explain how we do it, just to make sure everyone's on the same page. You want to find Z alpha over 2? What do? Yep, this is where I better pause and let you guys get to work. I'll give you a hint. You need the critical value, yeah. So the picture I'm drawing, right? What's the confidence level we want?
80%.
Okay, so you guys have to find this Z alpha over 2. I'll tell you what you're going to do to start. Start out by drawing this, and let's work maybe with someone near you. And this is the very start, is that there's going to be an 80% confidence this time. All right? And I'm going to shut it down here and walk around and let you guys compute Z alpha over 2 and finish the problem. So you guys are starting to tell the difference now between Z scores and areas. I mean, I agree there's 10% area over here and there's 10% area over here. And that's the Z alpha score I want, right? So I can say Z alpha over 2 is the inverse norm of what?
Negative 1.281.
Oh, that's what you got.
Yeah.
I'm still working it out. I'm going to do inverse norm. I'm going to say of 90%. Does that make sense to you guys? Because that way it'll be positive. I could do 10%, it'll be negative. So if I do that, I mean, either way is fine, because you're going to do plus or minus anyways, right? So if I do that, I get inverse norm
Yeah. 1.281.
of 0.90. Yep, 1.28 is the critical value. Okay, so I'm going to throw that into our formula. We got the 1.28 right here. And then, yeah, Sarah was asking me, what about E? Do we know E from the problem? Let's look carefully. E stands for the margin of error. Do you see what it says? It's up here. It says, in order to be 80% confident that your estimate is within 3 percentage points of the true population percentage. 3 percentage points, right? So remember how confidence intervals work. It's like, the way a confidence interval works in general is P hat plus or minus E, right? We want P hat plus or minus 0.03. That's what they want, 3 percentage points. So that's the margin of error. 0.03 is what we're going for. Basically, they told you how big they want the net to be, within 3 percentage points of P hat. And so if this is my formula for n, now I can just type it in the calculator and see what I get. Let's see what we have. So we have, well, if I go to the formula here, let's see, it was 1.28. Oh, but that should be squared, right? Because Z alpha over 2 is supposed to be squared. So I'll hit the x squared key. And then times 0.84, and then times again 0.16, and then divided by what? Well, yeah, so we want 0.03, but we want to square that also. And so I'll hit the x squared key again. And that should be the sample size, right? So if you want to be that accurate, it says you better survey how many flights?
Oh my gosh.
245 flights, right? You want to survey more than needed, if anything. Maybe 250, right? But 245 would be enough if you want to be that accurate. You guys follow?
Yeah, I just didn't plug mine in right.
Yeah, on the calculator.
Yeah, I'm like,
So I'll take a look at that in a second. For everyone else, I want to show you what Part A said. You guys, Part A, there was a problem with using the formula. Because what did it say in Part A?
Assume nothing's known.
Nothing is known. What do you know in Part B that you didn't know in Part A?
The percentage that was known.
Yeah, so in Part B, they gave you P hat, right? Which, by the way, also automatically gave me Q hat. Now think about using this formula in Part A. I'm going to go to Part A now. When I think about Part A, all right, P hat is, I don't know. And so Q hat is, I don't know. What we do if we have no idea what P hat and Q hat are, is we'll take the worst case scenario. The worst case scenario for the sample size we need is when P hat and Q hat are both 1/2. So I'll tell you what you want to do. Assume each is 50%, okay? I'd like everyone to do the problem again, assuming that P hat and Q hat are 50%, and I'm going to walk around and help those that had trouble with the calculation, and we'll go from there. Yeah, I'd like to see that, actually. So it's interesting because why is it bigger? I mean, the only thing we changed was these two numbers, right? By the way, if you think about it, we made them each 1/2, right? What's 1/2 times 1/2? Yeah. 1/2 plus 1/2 is a whole. What's 1/2 times 1/2? A quarter, right? Here, let me do it on the calculator for you. Right? I mean, I just asked you, what's 0.5 times 0.5? And we said that's 0.25, right? If you think about it, that's in the formula. 0.5 times 0.5 in Part A. But in Part B, the other one we did, you guys, up in the formula, I don't have 0.5 times 0.5. I just have this. See the 0.84 and the 0.16? Here's my question, guys. When I do 0.84 times 0.16, is that bigger or smaller than a quarter? Exactly. And that's why we had a smaller sample size when we knew that information. So, your formula sheet is funny. They actually give you extra formulas. See that one at the bottom? Look what they wrote. They just replaced the P hat Q hat with a 0.25. Why'd they do that? Because if you don't know what P hat and Q hat are, you're going to assume they're both 50%. That's like the worst case scenario. Anything else, you're going to get a smaller sample size. So I can go ahead and type that in, right? Here, let me go back to the calculator and get the same value you got. So I guess, again, if I type the same thing in, but instead of this 0.84 times 0.16, I'll just type in, let me delete some of this. 0.25. Oops. There it goes. 1.28 squared times, I could just type in 0.25 because I know that's what 0.5 times 0.5 is, divided by 0.03, hit the squared key again, and I'm in good shape. You guys got 455, right?
can you do it the other way? Put the 50 there instead.
Well, okay, so if you want to do it the other way, right, you don't need 0.50, you need 0.50 times 0.50.
Okay.
right? Because we're assuming p hat is 50%, but that also means that q hat is 50%. And so if I throw in my 50 here, but then I also throw in the 50 here, that should give you the exact same answer, right? And it does. Okay? So that means if we want to be 80% confident and we don't know anything, so the answer to part A, same thing, but we're going to get n equals 456 flights. Guys follow? Amy?
Where'd the one more come from?
Where'd which one? Oh, where'd the 1 come from?
One more, it was 455.
Oh, you're right. Well, you asked why did I put 456? Now, that's a good question. Because it says the sample size needs to be 455.11 flights. So you tell me, how many flights should I survey? If you tell me 455, I'm going to say that's not enough. It's supposed to be 0.11 higher than that. So I upped it by 1.
Okay.
Does that make sense? I mean, in a real study, I might up it by 5 in case we have to throw a few out. You know, so maybe I'd survey 460 flights. Right? It's okay to have a few too many, but if you have a few too less, you don't have that confidence yet. That's what's going on with that. Oh, we didn't answer part C of the problem. What did it ask? I saw it, but I only briefly looked at it. Given that the sample size is relatively small, okay, can you select Southwest flights between New York and San Francisco? What do you think about that? Would that be a good way to do your sample? Say, I only need 455 flights, so I'll just choose the flights between New York and San Francisco. Would that be good? Why not, Russell?
Because if you're looking at, like, in B, you're looking at 245 flights. And that's, you know, relatively, when it comes to flights, it's maybe, 2.5 to 3 hour flight.
Yeah.
So there's not going to be that many right away, so it would take even longer to.
Well, but they're talking about over the course of a year, right? Look at the last study they did, Part B. It took them a year to do their study, right? So now they want to update their study, make sure they're still on time. I guess the answer to C is no. Bad idea, Southwest. But let's see if I can explain why. It has to do with stuff in Chapter 1. We said that all these formulas we're learning work if you have what kind of sample?
Simple random.
Yes. Yes, yes, yes. Part C. Here's my answer, guys. I think this is important to understand. These formulas are valid for a simple, random sample of flights. Now, if you just say, hey, how about each day, we'll just check if the New York-San Francisco flight is on time. You know what that is? That's called a convenience sample. That's where Southwest said, hey, I'll just check that one. Because you know why? Because that pilot always wears a watch. I know what that pilot does. She's got him. And plus, what if the pilot that does that one is really good at getting people there on time? You know? Or what if they tend to put the newer planes on those long routes? But if you do these short routes, maybe you have older planes that need delays because they have to get serviced. You know what I mean? So that's not, if you want to do a valid survey, and this point keeps getting made over and over again, you need to somehow randomly sample those flights. Southwest should really have a list of all their flights. and somehow randomly select. But how many would they need? They would need 456, according to our calculation. You guys got that? I think that's enough that you should be able to answer any homework question at this point. But I know you guys worked on the homework, so I'm happy to take questions before we move on to something else if you want. Okay, I'm doing 17. That's the plan? All right, when you guys look at that, what are we supposed to do here? It doesn't tell me the confidence level? What are the directions, guys? What does it ask us to do? Well, let's see. Previous page probably says it. It says, okay. Express the, no, right here. In exercises 13 to 16, that's not it. We're doing 17. So what are the directions? Oh, part A. Oh, I see. They have different parts. Okay. What is the best point estimate of the population proportion of girls born to parents using the XOR method? That's easy. Basically, they're telling you compute p hat, right? So for 17, how do we do it? $879 divided by 945, correct. So p hat is 879 divided by 945, and you said you have that, Joanne? 0.930. So 93% of the time, the babies with the XOR method came out to be girls. So is their method working? Well, it's not perfect, right? You're not guaranteed a girl, but 93% of the time is certainly a lot bigger than, say, 50% of the time, which is close to that. Are there more girls than boys born? Does anyone know the stats in the United States? 49%, which way? Male? 51% males. So more males are born in the U.S. Okay. Is that U.S. or world? World. That's world. See what we have here. Part B. Use the sample data to construct a 95% confidence interval estimate. This is exactly the same kind of idea, right? So how do I do it? I know I need to, I have p hat. What's the other thing we need to compute, guys? Margin of error, E. The formula for E is Z alpha over 2 times the square root. I bet you have this formula memorized at this point. Yeah? Square root of what? P hat, Q hat over N. There it is, right? So that's the margin of error. The funny thing is, they said 95% confidence interval. I have something else memorized also. Yeah, that's what I was going to say. That tells me right away Z alpha over 2 is 1.96. Now, how do I really do it? How did I get that 1.96 so fast? Let's go through the process again. What do? You say, well, here I go, right? Let me draw my picture. I know that if I have 0.95 in the middle, then alpha is 0.05, right? And so I can do 0.05 over 2 is 0.025 on either side. Then you use inverse norm. Are you guys with me enough that I don't have to do any more? Okay, so that's 1.96. Times what? Square root of. Well, p hat we have. That's 0.930. We have that. Q hat we have. Oh, no, we don't. Oh, but we kind of do. What is Q hat? 0.07. Yeah, if this is 0.93, that's 0.07. That adds up to 100. Over the sample size, we have that too. 945. It's like once you start, it's funny how much, remember how long it took me to explain this? But once you learn it, cranking out the problems doesn't take long. All right, so let's get that margin of error. Did you guys compute that already? What'd you get? Did anyone else get 0.016 for the margin of error? Okay, I'll say that that's it. 0.016. And so I claim that the actual confidence interval, P is going to be between, well, we need to do 0.93 plus 0.016, and we need to do 0.93 minus 0.016. And so I claim my final answer would be P is, well, the upper bound would be 0.946, and the lower bound would be, I guess, 0.914. How's that look, guys? Okay? Sierra, how's that look? You asked. Does that make sense? Cool. And then was there a part C? I think there was. Oh, based on the results, does the XORT method appear to be effective? Why or why not? What did you guys say for that? Yes, I guess I decided that as long as I show you two different kinds of confidence intervals, that's enough. And later, I know some of you have to take a statistics class later. Some of you will take it in graduate school. I know that will happen. And I will warn you that when that happens, I'm sure you will estimate lots of things besides population proportions and means. Okay? You will see other kinds of confidence intervals. But as long as you've seen these two, I feel like, honestly, you can go from there. You'll know what they are, and you'll understand the differences, and this ought to be enough. All right? So again, I'm going to flash quickly through the slides, but I will pause and write some things down that I think are important for you to take note of. Okay? Now, key concepts here. Number one, I would say write that down, except I think you already know that, right? Do you guys know what X bar and mu are at this point? I think I've been trying to make a point of that, right? Which one's the parameter? Careful. Which one's the parameter? You're trying to give me a hard time. Thanks, Joan. Right? So again, the goal here is to estimate, so estimating mu with a confidence interval. That's the game. And so this is chapter 7, section 3, right? We want to estimate the population mean with a confidence interval. And I will tell you what it's going to look like. Mu is going to be bounded by two things. We just said that the best point estimate, if you have to give a single point, the best we can do is take the sample mean. Now, why am I leaving space? What am I about to write? I'm going to write plus a margin of error, and I'm also going to write minus a margin of error. So that's what it looks like. Now, here's the big difference. The margin of error has a different formula when you're estimating a mean than it does for a proportion. So you can't write down z alpha over 2 here anymore. Right. We'll see that here. The big difference, these are points I'll make in a second. I'll come back to them. There's the big difference. We're going to use something called the student t distribution. We've seen this before. Okay? So let me skip ahead to the formula. E doesn't equal z alpha over 2. It equals t alpha over 2 times s divided by the square root of n. So let me write that down because that's new to us. E equals t alpha over 2 times S divided by the square root of n. I know you don't know what T alpha over 2 is. I'll explain that shortly. Do you guys remember what S stands for? Standard deviation of what? Of the population or the sample? The sample. Yeah. For population, it was a sigma, right? And you know what n is, so that's fine. Okay? It's kind of interesting they wrote it this way, this formula. You could write it a different way that I think actually makes more sense. But this is simplified. Should I show you what I think makes more sense? Yeah, I should. I just have to. We'll use this formula. But I just kind of think it would make more sense if they explained it this way. It's E equals T alpha over 2 times a big square root. Do you remember what we did the square root of for the other formula? Remember what it was? P hat Q hat over n. Well, what it really is, guys, is this. The square root of S squared over n. S squared is the variance. That's what it really is. But I think what they did is they said, let's give them a simpler formula, so they just square rooted that. But they didn't show that. Okay? Oh, and there's one other thing you need to know. You will see this on the formula page. df equals n minus 1. Okay? df stands for degrees of freedom. It does sound like an album? Maybe it should be. Yeah.
This is what we're going to use.
Yes.
Oh,
7.3.
so.
So what's the difference now? 7.2, we were estimating a proportion, a percentage, right? We were estimating P. Here we're trying to estimate a mean. So it's a different formula. All the stuff is stuff I've seen before except for this, right? T alpha over 2. We never talked yet about the... Oh, actually we have. We did talk about the T distribution. You just don't know where. I'll show you. Ready? Let me show you where that comes from. I'll go up a slide. Oh, by the way, they say T alpha over 2 is found in table A3. That's true. But you know me, I don't like using the tables anymore. That's kind of ancient. We have the calculator. We'd probably use that. Okay? But if you want, there are tables for T also, just like there's tables for Z. Okay. So anyways, what's happening with the T distribution instead of the normal distribution? See, yeah, that's another way of writing it. We've seen that before, the plus or minus. Here's the picture that kind of shows you what's going on. You guys see that blue curve on top? That's the normal distribution. The T distribution is either the red one or the orange one. That's two different kinds. There are many kinds of T distributions, but every one of them looks a lot like the normal distribution. It's just a little bit smaller and wider. Do you see how it kind of spreads out a little bit more? And you'll notice that n equals 3, that makes it wider. When n equals 12, it gets more narrow and tall. If I did n equals 100, that would be really close to the standard normal distribution. Actually, the law of large numbers, right? Actually, the central limit theorem we talked about tells me that when the sample size gets big, whatever kind of distribution you have should start looking more and more like the normal distribution. So you could see it here. But basically, the reason you need degrees of freedom is it does change the values that we compute. Hey, you know what? I am going to go to the table for just a minute here, because I think that looking at the table can help you make a little sense of this. Here. Let's open up those tables. So where are they? I guess if I go here to the bottom page, the barefold tables. Let's do that. Okay, here's the z-scores, right? So we have negative z-scores, positive z-scores. And then here's the t-distribution. They're giving me the critical values. Hey, by the way, this is an interesting chart. It says area in one tail or area in two tails. Guys, for confidence intervals, we've always been talking about the area in two tails, right? Let's go to my favorite one, 95% confident interval. That's right in the middle here, because alpha, the significance level, is 0.05, right? And that means area in each tail is 0.025. See that middle column? Does that make sense to you, those two numbers? Okay. These numbers probably don't make much sense to you, but as the degrees of freedom goes up, you'll notice it's getting smaller and smaller. But what I want to point out is the very bottom of the page. Look at this. If you have 100, the critical value is 1.962. If you have 200, it's 1.961. And anything bigger than that, they say 1.960. Have you guys seen that number before? 1.96? That's the critical value for the normal distribution. So the t-distribution, if n is large, it's basically the normal distribution. There's no difference. But the problem is that a lot of times we're going to do samples that are small. And if the samples are small, the distribution gets pushed out. The critical values get pushed out some because of that. It's going to change the confidence interval when you're talking about means. So we should see an example of that, I think, and then we'll go from there. By the way, we have seen this before because you guys have seen this formula before. X minus mu divided by s over the square root of n. Remember doing that? When we studied the central limit there? We used to divide by the square root of n when we were talking about sample means. Okay, so you've seen this before. You were actually using the t-distribution. We didn't call it that. But that's what you were doing. So, they want me to find t alpha over 2 when I do one of these problems. So I have one picked out, and then we'll go from there. Oh yeah, problem 12 from this homework. It says, refer to the chapter 3 problem. The mean, so remember we were doing the chocolate chips? We showed you guys that one, right? Pick up Chips Ahoy. How many chips are in it? It says the mean is 23.95 chocolate chips, and the standard deviation is 2.55. Construct a 99% confidence interval estimate of the mean number of chips in a Chips Ahoy cookie. That's what the problem says to do. Okay? So, you're going to do the same kind of thing that you've always done. We're going to have to do this one tomorrow because we're running short of time. But I can show you one thing, okay? On the table, I should stop. We're at 9:15. We'll pick it up here tomorrow, guys. I think we have enough for now.